So now we finished describing motion. We are going to start talking about causing motion. So Newton had 3 laws. Actually, Galileo had the first 2, but because he didn't know the third, and the third completes the set, that's why they're called Newton's laws. So we have the first law, which is often said, an object in motion remains in motion, and an object at rest remains at rest unless acted on by an outside force. So that's the long version. The really short version, so these are all equivalent, is inertia. Objects have inertia. My favorite way, actually, of saying this is objects want to keep doing what they are already doing. They are already doing. Wish I could write faster. So if an object is stopped, it wants to stay stopped. You have to apply an outside force to make it start moving. If it is already moving, it wants to keep moving at constant speed and the same direction. If you want to change either of those things, make it turn, make it speed up, make it slow down, you've got to apply a force. So that's the first law. Second law is our one and only equation. Acceleration is equal to net force divided by mass. So we know what acceleration is. Acceleration is the rate of change, or the derivative, of velocity. It goes with the first law. If you have an outside force, you're going to change the motion. Changing motion means you're changing velocity. You're accelerating. The amount of acceleration depends on how much force, net force, are you applying, and how massive is the object. The bigger the net force, the bigger acceleration. The bigger the mass, the smaller the acceleration. Now, I will remind you about net force. Force is a vector, which means it has a direction. So if you have a 10 Newton force to the right and a 2 Newton force to the left, the net force is only 8 Newtons. If you have a 10 Newton force to the left, it completely cancels out. There's 0 net force. Now that we have lots of vector knowledge in this course, I could even give you a situation like one force is 10 Newtons at an angle of 30 degrees and another one is 40 Newton, I made that the same length. So 10 Newtons, but it's at 40 degrees. So what's the net force? And you would do your components and you'd cancel some in the vertical direction, you'd add some in the x direction, and you'd end up with the net force, and then finally you could put in the second law. We won't do a lot of that, but we will do some because we have to. Often included when we teach the second law, we talk about the difference of mass versus weight. Mass is how much matter. So it's equal to number of molecules and type of molecules. Number of molecules and type. Weight is the force of gravity. And the force of gravity is equal to the mass, how much matter, times the local gravitational field. Now, one of the things we did not talk about last year, but something I am going to bring up this year, is that this m and this m are the same thing. Now, it may seem obvious, we're using the same letter, but it didn't have to be this way. That the amount of gravitational force depends on the same quantity that is in the denominator of how much acceleration we get out of a net force. They didn't have to be the same. This is called inertial mass because this is how much this object resists changes in motion. How much inertia does it have to try to keep the motion it already has? So this is inertial mass. This is gravitational mass. If we measure the force of gravity and we measure the acceleration due to gravity and we divide them to get this mass, every test that has ever been done, these two end up being identical. But they do actually have different definitions. This is the mass that produces the force of gravity by interacting with another object, and this is mass that resists change in motion. They are the same as far as we know, but they're actually two different ideas that ended up being equivalent. Let that tickle your brain for a little while. And then we have the third law. Again, it's often written for every action there is an equal and opposite reaction. The problem with that, and as I've talked about last year, in English, reaction means something that happens because of something that somebody else did. So if you cheat on a test, I call your parents. If you break something at home, your parent gets mad at you. But the third law of physics means for every push, at the exact same time, the thing that's being pushed pushes back with the same amount of force and pushes back just opposite in direction. So if A pushes B to the right at the exact same time, B pushes A to the left with the same amount of force. So when I push this pen, that obviously doesn't require much force from me. That pen pushed me back. Now, the pen moved, I didn't move. Not only do we have a huge mass difference, but because it's the same force, it's not the same resulting change in motion. Let me get those back on the screen, the second law. Because we have such different masses with the same force, we have very different accelerations. Secondly, that's not the only force on me. There's a lot of friction between my shoes and the floor. And so that friction, that static friction force, is more than enough to hold me in place against this pen. But if I was in outer space and I was stranded and I was holding this pen, if I threw this pen away from me, I would go backwards. Now it'd be a tiny amount of acceleration and it wouldn't last for very long, so it'd be a very tiny final velocity, but I would be moving. And the more mass I could throw away from me, the faster I would move backwards and get back to my spaceship, for instance, if I were stranded. Okay, I'm going to take a quick look to make sure I hit everything on... one more. I knew I was going to forget this. There are a bunch of different kinds of forces, so I want to remind you of their names. We've already covered weight, which is the same as the force of gravity. We also have tension, which is the force by a rope or a cable. We have normal force, which is force from a surface like the floor or the table. We have friction force, which we will talk about in a couple of units. The first couple of the first couple of assignments are frictionless. We'll get to friction later. And then we do have spring force, the force from the spring. And that's the only extra equation I'm going to pull up now. We did this last year. The force of a spring is equal to K, the spring constant, times X, the spring stretch. So the spring constant measures, is this a tough spring to stretch or compress, or is it really easy to stretch or compress? So it can be a big number, it's hard to stretch or compress, or it's a small number. X is the amount of stretch. And So you're going to have a problem where we hang a weight from a spring, and I want you to figure out the spring constant. So if we have weight on a spring, and then the object is in equilibrium, the weight, the force of gravity, must be equal to the spring force. And then you can use that to solve for the spring constant. So basic ideas of Newton's laws, the three laws, mass and weight and spring force. You have a problem set on them. Then next time.